Now it's time to continue our discussion on matter and its properties. First of all, when you classify matter, you can classify matter in several different ways. And one way is to classify it according to its composition. A pure substance is any substance that has a constant composition. That is, all the atoms in that substance or all the molecules in that substance are the same. And these are three examples of this. In the first block, you have what looks to be sulfur of some type. And sulfur is composed entirely of the single atoms of sulfur. Now, so a pure substance that can be broken down into something different is called an element. And an element is made up of atoms. Compounds, on the other hand, can be broken down, and they are made up of molecules. And so a compound is a pure substance that can be broken down. Now in the picture here, what they're doing is they're heating this and changing it, and therefore it can't be sulfur, as I said before, because you can't change an element. And so it must be some sort of compound which with heating changes meaningfully. And so pure substances that can be broken down are called compounds and are made up of molecules. A mixture is a combination of two or more types of matter that is brought together. Now, mixtures can take several different forms. On the left here, you have what's known as a heterogeneous mixture. And a heterogeneous mixture is called a heterogeneous mixture because, as you can see in the sort of microscopic view, it's not uniform throughout. And this example is a combination of oil and vinegar in a salad dressing. On the other hand, on the right, we have what is known as a homogeneous mixture. And a homogeneous mixture is a mixture whose composition is unchanged throughout. And you can see that in that red block or gray or orange block, there's really no differences. And so this is an example of a homogeneous mixture. And so matter, you can ask yourself the first question, does it have a constant properties and composition? If the answer is yes, then it's a pure substance. Once you've said that it's a pure substance, then the question is, can it be broken down or simplified chemically? If the answer is no, then it's an element. If the answer is yes, then it's a compound. If the answer to your first question, however, does it have constant properties and a composition? If that answer is no, then it's a mixture. At which point you look and you say, is it uniform throughout? And the answer is yes, then it's a homogeneous mixture. If the answer is no, then it's a heterogeneous mixture. Now here's an example of a compound. It's a compound that can be and we know it's a compound because it can be broken down through chemical means. And so what is happening in this picture is what's known as the electrolysis of water. If you take water and you apply an electrical current through the water, you can split the water molecule and produce hydrogen and oxygen. And that's what this diagram is supposed to show you. Symbolically is shown on the right here, and then the actual process macroscopically is shown on the left. And what occurs on the left, what you would see if you were actually doing this experiment, is bubbles forming right above where the minus and the plus sign are. In this area right in here, you would see bubbles forming as the current is put in here. And then more time would pass, this water level would fall in both of these, and the oxygen side would always be half as big as the hydrogen side because there are two hydrogens for every one oxygen molecule in water. Now, there are two types of properties. There are physical properties and there are chemical properties. First of all, we're going to talk about physical properties. Physical properties are when something changes in its nature, but it does not change in its essential composition. So A here a physical change has occurred because the solid becomes a liquid, but the wax is still wax. And that's the important part when you're talking about a physical change. Physical change does not change the actual underlying compound and what it is. On the left here, steam condenses on the top of this cooking pot so that vapor becomes liquid. But in both cases, the vapor and the liquid, you still have water. Chemical changes, on the other hand, occur when something is fundamentally changed in its very nature. On the left here, we have iron, which is changed chemically to something known as rust. And on the outside of this, you can see little areas of the preserved metal underneath here. And then on the outside, you have this rust here. Now, what is rust? Well, rust is an oxide of iron. So you have real iron element here, but then a chemical process has occurred here. So on the outside here, you have iron oxide, which is called rust. Now, chromium, on the other hand, which is shown here, you'll notice it doesn't have all this rust on it. And that's one of the reasons it's used in this situation. Now, this is not pure chromium. This is chrome plating on the outside of another metal, which is much stronger than chrome. But chromium is used because it does not undergo this chemical change. Here are some more examples of various chemical changes. This A represents copper, which is these wires right here, and this liquid is also copper. In the presence of, the wire is copper and the liquid is nitric acid. A chemical change occurs and forms something known as copper nitrate, and a gas, nitrogen dioxide, is formed. So that's a chemical reaction, and both the copper and the nitric acid have undergone a chemical change. Any combustion reaction, anytime you burn something, that is a chemical change. And so you start out with a piece of cellulose, and you get it to a certain temperature, it combines with oxygen and begins to burn, and then water vapor and carbon dioxide come off as products of that. This is an example of red meat that's being cooked, and when it's being cooked, what happens is that the iron in the myoglobin oxidizes and turns brown. And then lastly, a banana turns brown because there's a chemical change in the chemicals in the skin of a banana that make it turn brown and cause it to look like this. And so there are certain warning labels that are put on various chemicals that help you to understand just what their chemical properties are. And there are 4 different ways of looking at it. First of all, the blue, and these are on the outside. You'll see these labels on the outside of drums of chemicals, and they help tell you about the properties of the chemical inside. And the first is blue. It's right here on the left here, and it's what health hazard it is. And the larger the number, the more dangerous it is health-wise. In this case, it's extreme danger. The orange is when it will burn. And again, the larger the number, the lower the temperature required to cause burning. In this case, this burns very easily. The third number is its reactivity. That is how volatile it is, or how likely it is to undergo a chemical reaction on its own. And again, the higher the number, the more volatile it is. And then lastly, in this bottom box is preserved for specific types of warnings, such as whether it's an acid, a base, or alkali, corrosive. In this case, it means use no water, which means it reacts badly with water. Here's one that you probably recognize: radioactive substances. Now, this is what's known as the periodic table of elements, and you will become very familiar with this after a series of future lectures where we talk about this. The periodic table of elements groups elements together according to their chemical properties. And it is done in such a way that you can figure out just by looking at its position on the table whether it's a metal, a non-metal, whether it would be more likely to be a solid or a gas. And so anything over on this side of the table, on the left of the table, is a metal. Anything over on the right of the table is a gas, a non-metal, excuse me. And then this little strip right here in between are what's known as metalloids. And metalloids are substances that have properties of both metals and non-metals. And we'll talk about this a great deal in future lectures because this is extremely important that you have this an understanding of this. Now I'm going to finish up the lecture, this last portion of this part and all of the next part, talking about various measurements. It's extremely important to understand measurements because we measure everything in chemistry. And this is just an opportunity to look at the relative relationship of various measures. For example, up here we have a meter, which is a measurement. These are all measurements of length. And a meter, if you look, is slightly longer than a yard. This is the meter is the Systems International unit. The yard is the British unit that's used in the United States. A centimeter, centa means 100 meter, so it means that it's 1/100th of a meter, or it takes 100 centimeters to make a meter. And down here you see you have 1 centimeter, and then you have 10 of these little things, which it would take 1,000 of these to make a meter. So each of these little ones are called a millimeter. And it takes 100 centimeters to make a meter. And 1 inch, on the other hand, which is, it takes 12 inches to make a foot, as you know. 1 inch is 2.54 centimeters. That's the same length. And we will do some conversions and show ways of doing conversions as well as we go through these various measurements. So these are measurements of length. These are measurements of volume. And again, it's the opportunity to look at the relative measurement of volume. The A here is a cubic meter, excuse me. That means it's 1 meter on the side, which means it's 100 centimeters on each side, which means there are 100 times 100 times 100 cubic centimeters in a cubic meter. And you can see up here, this cubic centimeter is quite small compared to the cubic meter. And a cubic centimeter is the same thing as something called a milliliter. And a liter is another form of volume measurement. So 1 cubic centimeter, or 1 milliliter, is relatively the same size as a dime, to give you some idea of the size. Now, another important process, and we will be talking about this a great deal throughout, and you'll get sick of me writing on your homework and writing on your quizzes, sig fig. And what that means is that you've not expressed your answer in the appropriate number of significant figures. So here's an example. When you look at any measuring instrument, it has a limitation of measurement. Now this, for example, is marked off in milliliter increments. So each small line represents 1 milliliter. Now it's very common when you measure something that it ends up being between 2 lines. And when you do that, you have to make a mental guess or an estimate of exactly how far. And by the way, when you measure, you always take the bottom of the meniscus as the point of measurement. And I would say here we're approximately 21.6 or 21.7 milliliters. Now the reason that we talk about significant figures is significant figures takes this into account, how much uncertainty there is in your measurement. There's a certain degree of uncertainty in that last digit. And so you have 21.7, so you have three significant figures. You could not possibly say, for example, 21.732167, because you couldn't be that certain. The best you can do is 21.7. And so you have three significant figures as the estimate for this.